Okay, good morning and welcome to the final day of the course and my last lecture. Before I start, I want to thank Dr. Raghavendra, Dr. Narasimhadhan, and other organizers of the course, NITK. It's been a great pleasure to come here and enjoy your company. The discussions we have had with you have been very nice. I also thank the other speakers, Dr. Shamlal and Dr. Deepu. Their presentations, including those of Dr. Raghavendra and Dr. Narasimhadhan, helped me recollect some of the previous material I had studied long ago in linear algebra, but also deep learning and CNN. Previously, I had some opinion. I had read some articles. I had made some opinions. Now I got a little better understanding of what is happening. I hope you also made the connection between the mathematics. We saw a representation of images and convolution as matrix operations, and what Dr. Shamlal showed in his lecture on CNNs, how the CNN matrix is arranged to perform convolution. It's essentially the same thing. So that gives me the understanding that CNN could be seen as a method of implementation of convolution. Now I have expressed some of my personal opinions. Those you take with your own judgment, a pinch of salt, as we say. So you have to take these opinions and then form your own opinion. So what I say is not the final thing. There are many other opinions, preferences. So I have said certain things about the way I would like to see things implemented, where you are able to explain what is happening. CNN and deep learning, they are moving in that direction, explicable methods. Previously, they were not. So things are evolving and changing, and so are these methods, the final methods that I'll talk about today to close this whole series of lectures. So again, it's been a great pleasure meeting you, and I hope you the typical term used is enjoyed. I don't want to say enjoy the lectures and seminars, but I hope you found them beneficial, and I hope you will find them beneficial further in your work. So in the title of the course, I added medical informatics and radiomics. Previously, I was simply saying digital image processing, computer-aided diagnosis. So now, for the first time, I added these terms. So I felt it is appropriate to discuss what is meant by them. The underlying concepts, techniques are the same: digital image processing, pattern recognition. But there are a few intricacies and fine details that we need to pay attention to. So what is the final goal of all of this? Personalized medicine. This is a rather new concept. Perhaps over the past 5-6 years it has developed, and it is still developing. So the aim of all of this is personalized medicine. So we have looked at computer-aided diagnosis, or CAD. What is that? We want quantitative and objective analysis of biomedical images via the application of computational procedures. In general, computers. The logic of medical or clinical diagnosis via analysis of biomedical images and data, signals and so on, can be objectively encoded and consistently applied in routine or repetitive tasks. This is what we want to do, and this is where we want to go, we are going, and that's the benefit: quantitative, objective, and so on. So the aim of CAD is computerized analysis of biomedical images, and that should be for computer-aided, computer-assisted, and not automated diagnosis. That's again my personal opinion and that of several other researchers. Where it goes, it depends on where the society goes. So what is this? Computer-aided analysis of biomedical signals and images, my main topics of research and teaching for many years, for 4 decades perhaps. Application of computational procedures, including digital signal processing, digital image processing, pattern recognition methods to enhance biomedical signals and images, filter, enhance, segment and characterize regions of interest, identify normal patterns and structures, detect abnormal features and diseases for computer-aided diagnosis. So this is the classification part. So note again, aided or assisted and not automated. So that is a mouthful to say. The easy way to say is AI, but everything has become AI. You touch a computer, oh, AI. So note that my lectures don't have those words, AI, DL, and so on. Even machine learning. I would like to have terminology very specific. What kind of a machine is it? What is it learning? So if you say digital signal processing, digital image processing, pattern recognition, pattern classification, no doubt as to what is being done. Very specific, and as engineers we should use specific and clear and precise terminology. So what are the essentials of engineering to be incorporated into CAD from the engineering perspective, not just computational? Scientific investigation and analysis, all scientists do that, analysis. Quantitative and objective analysis, mathematical modeling, optimal design of components, systems, and processes. Now moving to engineering, in engineering we do more of synthesis. We do analysis, but then we do synthesis. So what I said is engineers create new things that did not exist before. How do you do that? By synthesis. We need to know all of this. And from there, or through all these steps, we come to synthesis of multidisciplinary principles and methodologies. Multidisciplinary is again important, and I'll emphasize that again. And then some more concepts specific to engineering, project management, efficient solutions to practical problems. We address practical problems, not some hypothetical issue that is floating in the sky. Real down-to-earth problems, and go and understand them, solve them for some practical good to the society. Innovation and creativity. So these are important in engineering. Create something new. And that is where engineers are different from scientists. Not to put scientists down. We are building on what scientists have done before, and we are also scientists. So the field of biomedical engineering, as I said, some 40, 50 years ago, there was no BME, and it was new when I started my thesis work at IISc in Bangalore in 1976. It has moved a lot from pure engineering from the early part of the previous century to what has been done over the past 50, 60, 70 years. From building bridges to implanting artificial ligaments, my colleagues in Calgary in civil engineering have developed artificial ligaments that could be implanted in the knee joint. So it's like a bridge. From electrical power plants to cardiac pacemakers that power the heart and run the heart. From railway engines to prosthetic limbs, machines that are controlled by the subject. From chemical and petroleum plants to artificial tissues and organs, tissue engineering. From computers to lab on a chip and control systems to manage diabetes and other diseases. So there are these insulin pumps that are controlled by measuring sugar through another device. And one of my colleagues in Calgary developed what he called an e-mosquito that would take a small blood sample every so many hours and keep monitoring blood sugar. From communication and control systems to CAD. So these are the basic engineering principles that have led to these biomedical applications. So clearly, there is an engineering component or ingredient in all of these. And if you step back and see what those same things relate to previously, you see the original engineering application. We require a broad background to get into biomedical engineering. We do all the physics, chemistry, math, statistics, and so on. We had only PCM, later on PCMB came, I don't know what it is now. But we also need to have some understanding of biology, anatomy, physiology, pathology, biochemistry. Material science is part of engineering. Sensors and instrumentation, we are getting into electrical, electronics, principles of engineering in general, knowledge of medical diagnosis and therapy by collaboration. You can read books. I read several of these books. But in collaborating and talking with the medical experts, we get to know more about this practical. Information processing and analysis, signals, images, data of any kind. What are the subject areas contributing to CAD? Not only engineering. I'll put biomedical engineering first, but medical physics comes equally there. Diagnostic medical imaging and radiology, DSP, DIP, biomedical signal image analysis. I can't leave out my areas. Statistical analysis and pattern recognition. So we need statistics, computer vision, computer and software engineering, ICT or information and communication technology, control systems, and diagnostic decision making. So these are all different subject areas, and each one could be a separate field of study by itself. There are degrees in some of these separately. The main steps of CAD we have seen. How do we approach CAD? We first filter or pre-process the given signals or images. We detect and segment regions of interest, extract features for quantitative analysis, select the best set of features, so we reduce the dimensionality of the feature set. Training of classifiers and development of decision rules, that is pattern recognition, pattern classification. That's what leads to diagnostic decision making. Of course, all of that is given to the medical specialist. I don't go and do that with the patient. So why use CAD is an important question. Manual analysis of medical or visual analysis of medical images, even by experts, is susceptible to some types of errors. And even for us, when we do manual analysis of anything, not only medical images, intra-observer errors or inconsistencies, inter-observer errors or inconsistencies, and some limitations of manual analysis. What are intra-observer? The same person, same observer, could be inconsistent in the application of knowledge. My interpretation could be different over time, today, tomorrow, next year, for the same input. Subjective and qualitative nature of analysis, that is the root cause of these issues. If you're subjective, just giving an opinion, oh, this is long, this is short, this is light, this is dark, that is subjective and qualitative. Environmental effects and distraction. You are sitting and analyzing, something happens, some noise, and a radiologist is looking at all these mammograms and something happens, turn around, come back. You have lost that concentration. You were already concentrating on something, and then you're distracted. And especially when it is a repetitive task. Fatigue develops when you have to analyze 200 cases in 3 hours in an afternoon setting. Each case having, as I said, 4 plus maybe 4 more, 8 or 12 images, mammograms. That's a lot to analyze, hundreds of them. So repetitive task and workload is heavy, and fatigue develops. And then the efficiency goes down. Not only for radiologists, for anybody, for any of us. Inter-observer, between us. You do something, I do something else, perhaps. Inconsistencies in knowledge and training. You were trained somewhere else, I was trained somewhere else. So there is some difference. Subjective and qualitative again. Differences in opinion and preferences. So you have certain preferences, you have certain thresholds to call something benign or malignant, true or false, fake or real. You have some threshold always. Your threshold is different from mine. Limitations of manual analysis, inconsistencies in identifying landmarks in images, coming specifically to medical image processing. Errors in landmark locations due to limited dexterity. I need to point something, but my finger is this big. I need to mark something, but my chalk or pen is that thick. I can't go down to millimeter, micrometer accuracy. Extensive time and effort required for manual marking and measurement of intricate details. So you need to go and measure. It takes time and effort. Limitations in the precision and reproducibility of manual measurements and calculations. There could be some errors and in precision and also reproducibility. You may say 3.1 millimeter now, but later on you will say 3 millimeters or 3.2 or something. Again, all of that relates to subjective and qualitative nature of manual analysis. This is all just talking, so I'm going a little fast. Okay? Is that clear? And you have a copy of this. So what are the benefits of CAD? Consistent application of established rules and methods. And these rules and methods are established in consultation and collaboration with the medical specialist who is going to use, the end user. Objective and quantitative analysis, the opposite of qualitative, subjective. We are doing objective and quantitative. Numbers, everything should be numbers. Objective meaning there must be some rule, some methodology, some mathematical principles involved. It's not just throwing numbers out. There must be an underlying model, principle, methodology that is sound. Numerical precision, accuracy, and speed of computation. But we should be careful. The computer may give you 32-bit accuracy, but you don't want to give 32-bit accuracy to the user. It may not be meaningful. So you will say it is 5.2 millimeters, not 5.2, 3, 4, 9, 10, and so on. You don't do that. Ease of repeatability and reproducibility. Run it again, you get the same thing for the same data. Immunity to the effects of work environment, fatigue, and boredom. But the computer doesn't care, keep throwing data and you get output. Can process hundreds of images offline also. Need not be online. So the CAD way to improve medical diagnosis, I prepared this chart telling you want to move from this via that to that. So qualitative analysis to quantitative analysis via computation of measures, features, attributes using image processing techniques. Subjective to objective development of rules for diagnostic decision using pattern classification techniques. Consistent to consistent analysis by implementation of established rules and robust procedures as computational algorithms. And from having inter-observer and intra-observer errors to improve diagnostic accuracy by medical image analysis, medical informatics, CAD, and all of these things we are talking about. So this is what we are designing and developing to go from all of these to all of those. But there are limitations of CAD. All of our efforts have some practical limitations, or they face practical issues. Difficulty in translating methods of visual analysis into computational procedures. The radiologist describes, oh, this is rough, this is speculated. It takes us months to years to understand that and to translate that into a computational procedure. The radiologist said these spicules and this and so on. And that became a master's thesis eventually. So it takes a few months. We cannot do it overnight. Understanding that and translating that into an algorithm that works with some efficiency, at least 75%. Difficulty in translating clinical observations into numerical features. Again, what is smooth, what is microlobulated, how do you convert them to shape factors? Difficulty in dealing with large numbers of features in a classification rule, what is called the curse of dimensionality in pattern classification. You don't want 10,000 features. Classification becomes difficult and inefficient. Maybe 100, okay, but can you reduce to 10? So you can manage the procedures well, get the most efficient combination of a small number of features. Small, depending upon the application, not one, could be 5, could be 10, could be 100 sometimes, but not hundreds and thousands. You may start with hundreds of measurements, but shrink it down by appropriate methods of feature selection and dimension reduction. Substantial requirements of computational resources. I'm not concerned about that. They ask, well, how much time did it take? But computers have been getting faster and faster and faster. So what took a supercomputer when Dr. Chowdhury was working on those collagen fiber images, we needed a vector supercomputer. Now you can do on your little some computer easily. So that's not a big issue, but annotated clinical databases. We heard that from our other speakers also. Dr. Shyamlal mentioned that just having data is not the thing. They must be annotated. I think Dr. Deepu also mentioned that. If they're not annotated, they cannot be used for training. There is unsupervised, yes, but there are difficulties, there are limitations. So it is good to have annotated clinical databases, but as I mentioned a few times, radiologists don't sit in the clinic drawing boundaries of tumors and calcifications or the hip bone and something else. Now they look at it and say, this is the situation. So this requires a lot of effort on part of the radiologist or medical specialist. If I do it and write a paper, no, that won't fly. I could do it and get it verified by the ophthalmologist or radiologist. Then it says it's some kind of a consensus or training, and that may be acceptable. But there must be the involvement of the medical specialist. In the end, we face large numbers of false alarms or false positives. They will be there. We need to reduce by including further methods for better feature extraction and classification. And that leads to increased recall rate. That is, if you give a false alarm and say there is something suspicious in this patient's mammogram, the subject is asked to come back and more tests and all that. That is called recall. You're asking the person to come back for more tests. That causes anxiety, costs, and various issues. As I mentioned earlier, mammography by itself, before CAD, mammography by itself was the cause of concern of increased recall rate. A number of women who went to the screening program to get mammograms taken were called for additional tests because the mammograms were not of good quality. And not many radiologists were trained in the interpretation that was considered to be the most difficult in radiology. That is why we started to work on that topic. So women were concerned that, I go there and mammograms are taken, they will ask me to go back, do biopsy, do this, that, and I don't want. So if you have an assurance that our sensitivity is high, we will catch cancer with a high accuracy, and our specificity is high, that is, normals are called normals with high accuracy. Both must be high. If I call everybody as having cancer and send them to more tests, the lab will make money, but the patient will not be happy. If I send everybody back home telling you are normal, then some of them will develop cancer and the effects of those diseases, and things get worse. So a good balance is required, but we must have high sensitivity and specificity. That is difficult. And difficulty in integrating CAD systems into established clinical workflows and protocols. The radiologist is already doing something, has been doing that for 10, 20, 30 years. The screening program has been running for 10, 20, 30 years. And now I want to go and stick my computer in. There's no place, and the protocol is established. You can't change that because it's established by the cancer board, and they have gone through many other studies. So it is difficult. Even if the radiologist wants it, how do you do that? Not that there is no space to stick a computer and a monitor. There is space. But previously, they were looking at films. There were no computers. Now they're all looking at computers. So I'll put another monitor there. So it has become easier and feasible now. Further limitations. A physician or medical specialist typically uses several items of information in addition to images and measurements. Images are used, yes. They also make some measurements using a ruler or something, a finger, whatever. Results of clinical and lab tests, physical and mental state of the patient, family history, socioeconomic factors. How is the patient appearing? Many of which are not amenable to quantification and rule-based processes. These are done through expertise of the medical professional. Okay? You can't put a number and say, I'll put that into a pattern classifier, A, B, C, D, 1, 2, 3, 4. You may put some textual description. So there are some methods to integrate text-based descriptors and numerical descriptors. But they are not easy, and perhaps not possible in some cases. So what we should recognize is biomedical signals and images are, at best, when they are perfect, indirect indicators of the state of the patient. They are not direct indicators. They are showing the manifestation of the effect of disease on that organ or system. They are not direct indicators like if you take a tissue sample or blood sample. They would be direct indicators or biomarkers. These are indirect. The results of image analysis need to be integrated with other clinical signs, symptoms, results of lab tests, and non-medical information by a physician. I'm repeating some of these things, but I think it is important to drive that point home. So the general background knowledge, expertise, experience, and intuition of the medical specialist play important roles in arriving at the final diagnosis. Most of us would agree with background knowledge. Yes, they have to pass MD. Expertise, yeah, they must have the expertise, experience. We don't want to go to a new doctor. In Kannada, it is said, ಹೊಸ ವೈದ್ಯರಿಗಿಂತ ಹಳೆಯ ರೋಗಿ ಒಳ್ಳೆಯದು ಅಂತ, meaning an old patient having had experience with the disease can give you better information than a new doctor. And that's a light saying in Kannada. But of course, new doctors, before they are licensed, would have gone through training and they know things. Now, this is where I'm coming to some personal observations, and I have talked about this with my medical colleagues too. So let me go back here. Intuition. Intuition is something that cannot be quantified. The expert, or you, when you're dealing with other engineering issues, will come up with some decision or some procedure, but you cannot explain it. It's intuitive. You didn't derive it mathematically, but there is a gut feeling as I say, okay, I think this works. This is the situation. Without being able to explain that and prove it. Scientifically, that is not sound. We said earlier you should be able to explain everything and there must be an underlying procedure. Intuition is not that, but still it plays a role. And I have again talked to my colleagues and they agree. Yes, there is, intuition does play a part, although it cannot be explained. Perhaps a minor role. But how do you take all of this information and come up with a diagnosis rapidly? There is something else that is happening, which is hard to explain and quantify and put in a computer program. So I have included this. I thought of removing it, but I have had some discussions and we will leave it there for now. Now, to the professional aspect and legal issues. Keeping in mind the realms of practice of various licensed and regulated professions. In Alberta, in Canada, in many states and countries, you have to have a certain degree. To practice engineering, you must have engineering degree. To practice medicine, you must have MD. To practice law, you must have LLB or whatever the degree is called. And then professional practice and licensing. You have to write some ethics and practice exams and about the bylaws and whatnot that govern the profession. And then you are liable. If something goes wrong, you are liable. So there is liability. So I'm licensed. I'm a PEng, professional engineer. I have a stamp. If I design something in my area, of course, I'm not going to design a bridge and stamp it. I can't do that. PEng doesn't say what kind of engineer. But if I go and design a bridge and put my stamp on it, no, I'll be in trouble. Similarly, I cannot go and give diagnosis, medical diagnosis. So I cannot claim my computer is giving this diagnosis. My computer is better than the medical specialist. No, that is wrong. And legal factors. Who is taking the responsibility for the final decision? It is the physician, the radiologist, the doctor, and so on. They are licensed. They have some insurance for liability. And the patient will go there. The patient won't come to the person who wrote the computer program. Cannot do that. If you make a measurement using a ruler, you are still making the decision. If something goes wrong, one cannot go and sue the person who made that ruler unless that ruler had some inaccuracy and simply said, this is 1 meter. That doesn't happen. The final diagnostic decision and communication with the patient in particular are best left to the clinician, physician, or medical specialist. So we won't step into that. What we expect is quantitative and objective analysis facilitated by the application of biomedical image analysis, medical informatics, CAD, and so on, could lead to improved diagnostic decision by the physician and improved healthcare for the patient. Not simply increase the efficiency, but the patient should see some benefit from that. That is the expectation. So going back to AI, is CAD AI? The answer is already, I have said no. But CAD incorporates and encodes and encapsulates This is our statement. The collective and collaborative intelligence and expertise of professionals from multiple disciplines, mine, my students, they're all engineers, the medical specialists, their associates. There are a number of people, if you look at the co-authors of my papers, there's a long list, at least 5, 6, sometimes more. So they're all professionals. All of them have put their intelligence into this. Radiology and diagnostic, medical imaging, engineering, computer science, physics, chemistry, math, biology, everything. So this is natural, not artificial. I want to argue against those terms. Natural human collaborative endeavor, not some computational machine doing something. Yes, we programmed it, but it is ours. So the intelligence is mine, yours, our collaborators, collective, collaborative. And the label artificial, I would say, is demeaning, it's insulting in such a setup. So we should recognize, admire, and respect the contributing professionals and their subject areas. So if I talk with the radiologist and learn all of these things that I've shown you, and then run away and say it is artificial, that's not right. So CAD is not AI. If you want, you can call something else as AI. So the terminology of AI may not appeal and may not be accepted by patients and the general public in the medical setting. I don't want artificial sugar. Does anybody want that? Unless there is a medical issue. In the regular situation, you don't want substitutes. You don't want chemicals in your food. Right? You don't want artificial flavors. I want the real stuff. I want real kesari. If they say I put kesari equivalent color, I'll send it back. I don't want that. So, artificial will not be accepted in food. In medicine, perhaps, when you go and get your diagnosis done and some treatment is being given to you, you want a real qualified person doing it. So in the medical setting, this terminology perhaps is not suitable and may not be, I would say, will not be accepted by patients and the general public. But CAD is developing. These are all developing fields. They've been around for some time. But there are things beyond CAD. We can do a lot more. Several areas of application of computers in medicine exist beyond CAD in the quest to improve healthcare. So towards personalized medicine, you have computer-aided so many things. I mentioned therapy and how the information from those Gaussian mixture models of tumors could help in surgery and planning for surgery, how detecting the spine could help in planning radiation therapy. The analysis of response to therapy, we saw those ligaments, those are sort of biomedical. It's not medical, there's from rabbits and so on, but the models apply, they can be extended. That's why those animal models are chosen. So response to therapy, which treatment is the best in terms of getting collagen alignment back soon? Prognosis, we haven't done that. Prognosis is what is going to happen with the patient next after this. That is an important step. It is coming, but we are not there yet. Patient management, clinical management, I'll leave that out. That's how you run your clinic and how computers could be used there. Treatment protocol, again, therapy, it is a protocol. So computer-aided analysis of all of these could lead to computer-aided treatment protocols being developed, and finally, computer-aided personalized medicine and preventive, or some people say, Americans say preventative healthcare. So personalized medicine, that includes diagnosis and treatment. Preventative healthcare, this is healthcare to say, okay, this has happened, we don't want this to happen again. How do we prevent that? For that, you need to know the prognosis. Where is this patient going in the next few years? And how do we stop any bad disease coming back later? These lead towards personalized medicine, but that's not all. We need informatics. Now, informatics, we have a few different types of informatics names and terminology in biology and medicine. Bioinformatics deals with the application of biology, physics, chemistry, math, statistics, and now I'll put computer engineering. Some will say computer science, some will say data processing. Let's call it computer engineering, to analyze and interpret biological data about genomes, physiomes, and this and that. Maybe only biological, not health related directly. Could be related to farms, animals, and so on. Agriculture. When you say biomedical, you're getting into medicine and healthcare, but there could be some bio component that might not be directly related to human beings, like the collagen from rabbits and so on. So there is a bit of something else that is not exactly directly related to radiology, medical physics, and human data. Finally, medical informatics, bringing medical sciences and computer engineering. Again, some will say computer science and data science and so on, together for improved healthcare and outcome for the patient. So again, healthcare should be improved, but how do you define it? It's not the physician making more money or the lab making more money, but the better outcome for the patient. Now, when you get all of these different types of data, or observations or measurements from images, signals, lab tests, and this and that, put them all together, then there is a package that's nowadays called a digital twin of the patient. All of my information, not my picture, but all of my biomedical information stored in some specific format that could help in all of those compute-aided, that long list. So a package of data related to the specific patient. We talked earlier about landmarking, atlas-based, and so on. Atlas is for the whole population. You could subdivide to female, male, age groups, and ethnic groups, and geographical groups, but still groups. Then we said we want to landmark the specific specific image of that particular patient and get measures of Hounsfield units of the spinal canal or whatever for that specific patient. So here, these are of the specific patient, not a general model, obtained using various biomedical sources of information, images, lab data, whatnot. It's referred to as a digital twin of the patient. A digital twin of a patient may be constructed to represent the patient's entire body or a specific organ, system, or structure. Could be very particular, not the whole body. You may not be interested in the whole body, just those parts that are having some issue. So the digital twin model may be expanded to incorporate external factors, including the environment and interactions of the specific patient. As I said, this presentation is only text and storytelling. I prepared most of this over the last 3-4 days, so I'm checking for any errors in typing or composition. But some of these were in my other presentations on biomedical engineering and CAD and so on. So I have pulled them. I have added some new material, which appears in the discussion in our new books. Incorporation of patient-specific information could improve the design and development of personalized healthcare for that person and therapeutic recommendations for the individual patient. So that is how you are moving towards personalized medicine, not simply what the textbooks say. So what is personalized medicine? It is defined as healthcare that is informed and guided based upon an individual patient's unique clinical, genetic, genomic, and environmental information, not just images and signals. Personalized medicine has been focused on an underlying knowledge of normal physiology of the patient, as well as pathology based on what is called omics, to facilitate preventive healthcare and strategies to guide therapy. So what are the omics? The omics are areas such as genomics, proteomics, metabolomics, and so on. All these omics. So these give you measures and data related to the patient, but through other tests. You cannot get these from signals and images. So the goal of personalized medicine is to optimize healthcare and the ensuing results for each patient. You are customizing patient care. Previously, we would get our clothes stitched by the tailor and specific measurements. Nowadays, we just go by and say medium, large, extra large, whatever, 36, 40, 42, some number. And sometimes it fits, sometimes it doesn't. And we just live with it. So now we want customization tailored to the specific patient so the patient can get better care. There are multidisciplinary approaches required here. One of the papers I read mentioned this, and I was happy to read this. The requirement of multidisciplinary approaches to diagnosis and delivery of healthcare to achieve the stated goal of personalized medicine has been emphasized. It cannot be done just by medical specialists or this or that or that. We need all of them, with particular attention not only to the omics, but also to biomedical sensors, instrumentation, data analysis, computational methods, informatics, and diagnostic support systems. That is what all of us do. Electronics, DSP, DIP, all of that. Okay? So this has been written by somebody else, not mine. So with the inclusion of a broad array of multidisciplinary techniques, biomedical signal image analysis, now I'm talking here, can make important contributions towards the realization of personalized medicine. This is one piece among all of this. Not the only thing. So what is radiomics? There is confusion in the literature. To emphasize the role of features and measures derived from radiological or medical images in diagnosis and therapy, the term radiomics has been introduced. Again, this is our interpretation to emphasize radiological input, but that's not everything. So radiomics is radiology and all the omics. It is not radionics, it's not radiology and electronics. It is not radiotics with informatics and radiology. It is radiomics with the omics, ending with OMIC. Because radio comes first, it is radiology. That's the main factor, all right, no problem. And that's where we do our business of medical image processing. But how do you go from radiology to radiomics? The intent with this terminology is to promote the combined use of quantitative information derived from medical images and the various omics fields. Not only in diagnosis, we're not stopping there, we shouldn't stop there, but therapy, follow-up, prognosis, preventive medicine, and extended healthcare, of course, personalized, customized, we already saw that. That's included. I didn't want to include all of those terms. So in discussions with my clinical collaborators, I asked these questions. What is radiomics? And I read some papers, and some papers simply said, oh, I'm computing 1,000 features, it is radiomics from medical images. That's not it. I can compute 10,000 features. That's not radiomics. Some have said so, and some definitions have said so. If you extract a large number of parameters from medical images, that is called radiomics. That is not correct. And we have done all these classifications you saw with the vertebral compression fracture. Dr. Marcelo Noguera Barbosa, he is a radiologist in that team. So we asked him, oh, you're putting your input, you're doing some classification, and we are putting all these features. Is this radiomics? He said, no. He said, that is not radiomics. There must be these factors. What is the effect of therapy? Did you design therapy using this? What is the effect? Follow-up. What is the prognosis? Can you predict what will happen next? And can you help in preventing and extending the health care? That we haven't done. There are bits and pieces sort of pointing in that direction. The possibility of doing those. But we haven't done. There are very few studies on this. As I said, many papers simply say that tag is determined by the number of features, which is not correct. And only diagnosis, that is not correct. How much has been done with all of this? very few. I'm still searching for good papers that actually demonstrate all of these. So it's left for you. Earlier I said the next generation should always be better than the previous one. That I also corrected myself and said it doesn't mean we are greater than our teachers. It simply means we are adding to the knowledge base, and the field is growing and developing. We are contributing, and so should you, the next generation, and the next to that. And some could be better than those who have passed before that. But they have contributed to that, to the base. So I think it is Newton who said, I can see further because I'm standing on the shoulders of giants. So there have been others, and we are standing on top of them or their knowledge base that they developed, and then we can do more. We cannot claim to be better than them. We couldn't have done this without their input. Without Professor I.S. and Murthy's courses on biomedical signal analysis, biocontrol, and various other instrumentation that he taught us, we wouldn't be here doing this kind of material. So radiomics as a field of study is what is being emphasized too. It is also, this terminology is intended to establish and promote a corresponding formal field of study. When you put a name, like physics, chemistry, mathematics, and so on, you're identifying an area of study, a subject area. An investigation of various biomedical measurements, attributes, and features derived from various sources of information. So radiomics is here, but there are still a few challenges. It's a new and developing area. Confusion exists in its definition, practical application, and interpretation. Practical application is made difficult by the lack of data as well as models and procedures for implementation. How do you get all of these prognosis and extended healthcare? We don't have such information. To build such databases or even examples and models will take some time. But it'll come. It's here. It's coming. And how do we put it into clinical practice is another question. And there have been all of these. We know CAD, we know computer-aided surgery, it's here. Content-based image retrieval, the hospital and radiology information system, picture archival and communication systems, DICOM standards, digital imaging and communications in medicine, database management systems. All of them are known now. Electronic health record is coming, it's here. HL7 is a new international standard, new meaning in the past 5-6 years, maybe 10. ISO, we know it's been around, the International Standards Organization, but now they are getting into this, HL7. Open Systems Interconnection, that is another standard that will facilitate this. So how do we put all of this together in the hospital? There are some practical issues, but it'll be done. There are standards being developed to help in this process, to realize this. And now we put in radiomics and digital twins. Those are relatively new concepts that have come up. So add all of these. So this is the general story. I have a couple of small illustrations. We talk about data, and I have a lot of data. And our other speakers, Dr. Shamlal and Dr. Deepu, also talked about gathering data. Just by having data, it doesn't mean much. So we first, anyway, in the stage of learning, we first collect data, observations, lectures. We attend lectures, take books, read. We take these objects, make measurements, and we process them. Just data processing. So we get measurements, features, attributes, descriptors, like feature extraction from images. We'll come one level up in this process. Then, as I have mentioned earlier, we need to distinguish between processing and analysis. You process a number of measurements, values, 1 plus 2 plus 3, 6, take the average, divide by something, 3, and you get 2. You got another number. So what does it mean? You need to analyze that. So you need to have some skills of analysis and interpretation, and then you got some information. So distinguish between data, measures, and information. This is just the input. Now you have some information about which you can talk. And we need to understand that comprehension is necessary. Just having the information doesn't help. So with comprehension, we develop some knowledge. Then we can say, okay, now I know something about this. Sometimes I make fun with my students, but sometimes either the joke doesn't go or they don't like it. When I was teaching signal analysis, a second-year course, I had 140 students, and I decided to write on the board. I could have done this. I have done this in signal processing, image processing, but second year I thought I should write on the board, like what Dr. Narasimhadhan did and Dr. Raghavendra did. I wrote on the board, and I said, you must write it. Writing is a part of the process of learning and perhaps will help you remember. The students didn't like that. They started taking pictures with their cell phones. So I would write this and then click, click, click. So I told them, well, you have taken the picture. If you want, I can stand and smile, or I'll walk out and you can take a picture, all right, no problem. But if you take a picture, it's in the memory of your cell phone. How do you transfer to your memory? You don't have a USB connector here, unfortunately, yet. It'll come. It may come, I hope. Yes or no, I don't know. How do you transfer from there to here? So you have to read and understand. Anyway, some of these things may not fly well with undergrad students. That's why I like grad students more. They will understand them. So knowledge comes with analysis and comprehension. Now the next level, before we can go to intelligence, artificial or real, artificial perhaps will not go that high, is design, synthesis, innovation, experience. So as engineers, we design things, create new systems. Synthesis, we put many ideas together. Innovation, there has to be something new. Otherwise, you can't write your paper, you don't have a product to sell or just to show. And experience, you must have some field experience in that area. Otherwise, you would be called a novice, and people may not have much confidence in what you're showing. That leads to creativity, intelligence, and expertise. So intelligence is at the top. From data you can just acquire. I can buy 100 books. That doesn't help me. Okay? So there are different depictions of this pyramid as to how you go from data to measurements to knowledge, but I added these as to what are the steps necessary to go from one level of this pyramid to the next. But it's a never-ending path, like all studies. When you get your BTech, MTech, PhD, you say you're done, but there is a lot more. This was in one of the greeting cards for graduation. It goes on. If you stop there, that's okay, but there is a lot more. So what do we want to achieve? We are talking about engineering for improved healthcare. I use engineering as a verb also. Engineering improved healthcare. That's what we want to do. We want to take all of our engineering principles and knowledge and experience and expertise and put it for improving healthcare and social benefits. So this gives us opportunities to learn new areas of application of engineering. Relatively new. It's been established, biomedical, but there are newer and newer areas of applications and problems to be solved. Collaborate with professionals in other fields of research and investigation, so we learn more of other areas, subject areas, other types of problems, how to address those problems. Contribute to a field with significant applications and benefit to the public, so we can put our knowledge to benefit of others, the general public, in terms of healthcare and well-being. Develop multidisciplinary perspectives and problem-solving skills, so we also learn in that process. So nowadays, this is emphasized. Previously, scientists were known to just sit in the lab and keep doing some experiments, chemists in particular, or mathematicians sitting and working with equations alone in the lab or office. That is not the case anymore. We need groups of scientists and researchers from multiple fields coming together to solve a real problem in the real world. that you may not even encounter or know about if you just sit in your lab or office and work with pencil and paper. That's fine. We need all of that. But in order to achieve something like improved healthcare, we need this collaborative and multidisciplinary approach and perspective. So we could contribute to healthcare and well-being of people. So Paulo and Marcelo are my collaborators in Brazil. We have talked a lot about radiomics as to what is it and where is it going. We started our collaboration many years ago, 25 years ago, starting with processing mammograms, detecting this and that, pectoral muscle, breast boundary, nipple, and all of that. And then suddenly this radiomics came up. I said, well, what is this? And then we had more discussions as to what exactly we want to do next. So that is what has contributed to this presentation. And also my collaborators at the University of Sao Paulo, many others, Manitoba and Calgary, especially the medical researchers have contributed to this understanding and all of these notes. So you have seen my website and you have my email. You're most welcome to write to me. So thank you very much for your attention, and wish you all the best in your research work and career.